worked at many large companies such as Amazon and Google. And now I'm working at one of the top Silicon Valley-based startups specializing in big data analysis. In this introduction lecture, we'll see what this course covers and what you will learn from this course. In the first section, we'll develop a conceptual understanding of virtualization technologies, hypervisors, and Linux containers. Then we'll see how Docker fits into the overall virtualization technology ecosystem. Then we'll get to know Docker server and client architecture. Next, we'll learn how to install Docker on your local computer. No matter whether you're using Windows, Mac, or Linux, you'll be able to follow along. Develop our understanding of some of the most important Docker terminologies, such as containers, images, Docker registries, and repositories. And we'll try out our first Docker workflow, where we'll pull an image from Docker Hub, create and run a container from the image. Then we'll take a close look at some of the useful commands to work with Docker containers, such as Docker PS and Docker inspect, etc. In section 2, we'll start by introducing an important Docker concept, image layers. Then we'll learn how to create our first Docker image using Docker commit command. Next, we'll look at a more professional Docker workflow, which is to use the Docker file to build Docker images, which we can run as containers. Then we'll deep dive into several important Docker file instructions, such as run, command, copy, etc. And once we create our own image, we'll daemon pushing our image to Docker Hub. Then we can pull that image from online repository to run on another environment such as staging or production. In section 3, we'll apply the knowledge we have learned so far to Dockerize a simple Hello World web application. Next, we extend our Hello World web application to a key value lookup service by incorporating Redis Docker image. You'll find out how effective it is to use Docker to build up applications with a microservice approach. Then we see how to use containers linkings, which allow containers to discover each other and securely transfer information about one container to another. And we'll take a close look at how container linking works behind the scene. We'll learn how to automate our current Docker workflow with Docker Compose. Then we'll cover more details about Docker Compose workflow, such as Docker Compose build and Docker Compose PS, etc. In section 4, we'll create some unit tests to test our Dockerized application and run those tests inside the Docker container. Next, we'll extend our Docker workflow, set up the GitHub account and CircleCI account to create a continuous integration pipeline in the cloud, so that any changes pushed to our GitHub repository will trigger a build on CircleCI. After the test is green, the Docker image will be automatically pushed to Docker Hub. In section 5, we'll start by learning some of the concerns about running Docker in production. Then we'll see how to deploy our Dockerized application to a production server running in the DigitalOcean cloud. Then we'll learn how to use Docker Swarm to scale Docker workflow and deploy our Docker web application across multiple hosts in the cloud. At the end of this course, I'm confident you will gain in-depth knowledge about Docker and general DevOps skills to help your company or your own project to apply the right Docker workflow and continuously deliver better software. You will go from zero to Docker Hero in 4 hours.
Hello everyone, in this lecture we're going to talk about how you should take this course and how to get support. A lot of slides provide practical information on how to do things. The source code for this course is uploaded to GitHub. We'll also keep the repository up to date with new and extra information. We have put most of the complicated commands we're using this course to the text lecture right after the video lecture, so that you can copy and paste those commands and try out on your own laptop. We also have a Facebook group called Learning DevOps and Level Up. Facebook group is a fantastic tool that we can use in so many of the communities we're in, and we hope it would be a great way for extending this course and adding more value to your learning. You can post your questions in the Facebook group and we'll try to get back to you as fast as we can. We also periodically share the latest trend in the DevOps world and some practical tricks we found useful. You can scan the following barcode or use the link in the next text lecture after this video lecture to find the group.
Technically, Docker is one implementation of the container-based virtualization technologies. Let's take a look at how virtualization technology has evolved over time. In the pre-virtualization days, we're using big server racks. Underneath, we have the physical server. We install the desired operating system on it. Then we run the application on top of the operating system. And each physical machine would only run one application. So what was the problem with this model? First of all, we have to purchase a physical machine in order to deploy each application. And those commercial servers can be very expensive. And we might end up only using a fraction of the CPU or a memory of the machine. The rest of the resources are simply wasted, but you have to pay for the whole hardware upfront. Secondly, deployment time is often slow. The process of purchasing and configuring new physical servers can take ages, especially for big organizations. Thirdly, it will be painful to migrate our applications to servers from different vendor. Let's say we install our application on an IBM server. It would take us lots of effort to migrate to Dell servers. A significant amount of configuration change and manual intervention is required. The rescue is the hypervisor-based virtualization technology. Let's take a look at this virtualization model. Underneath, we have the physical server. Then we install the desired operating system. On top of the operating system, a hypervisor layer is introduced which allows us to install multiple virtual machines on a single physical machine. Each VM can have a different operating system.
For example, we can have Ubuntu installed on one VM and Debian on another.
In this way, we can run multiple operating systems on a single physical machine, and each operating system can run a different application. This is the traditional model of virtualization, which is being referenced as the hypervisor-based virtualization. Some of the popular hypervisor providers are VMware and VirtualBox. In the early stage, users would deploy VMs on their own physical servers. But nowadays, more and more companies have been shifted to deploy VMs in the cloud with providers such as AWS and Microsoft Azure, which means we don't even have to purchase physical machines upfront. There are some huge benefits with this model. First of all, it is more cost-effective. Each physical machine is divided into multiple VMs, and each one only uses its own CPU, memory, and storage resources. We pay only for the compute power, storage, and other resources you use, with no upfront commitments, which is a typical pay-as-you-go model. Secondly, it's easy to scale. With VMs deployed in the cloud environment, if we wanted more instances of our application, we don't need to go through the long process of ordering and configuring new physical servers. We can simply click the mouse and deploy more VMs in the cloud. The time taken to scale our application can be reduced from weeks to just minutes. This results in a dramatic increase in agility for the organization. This hypervisor-based virtualization model has obvious advantage over the one application on one server model, but it still has some limitations. First of all, each virtual machine still needs to have an operating system installed. This is an entire guest operating system with its own memory management, device drivers, daemons, etc. When we're talking about a Linux operating system, we're talking about a kernel.
For example, here we have 3 host operating systems and 3 kernels.
Even though they can be 3 different kernels, we're still replicating a lot of the core functionality of Linux. In this traditional hypervisor-based virtualization model, we have to have an entire operating system there simply to run our application, which is still not inefficient. Secondly, application probability is not guaranteed. Even though some progress has been achieved in getting virtual machines to run across different types of hypervisors, there is still a lot of work to be done there. VM portability is still at an early stage. Finally, the container-based virtualization technology comes out. Docker is one implementation of the container-based virtualization technologies. Let's take a look at the diagram here. Underneath, we have our server, and this can be either a physical machine or a virtual machine. Then we install our operating system on the server. On top of the OS, we install a container engine, which allows us to run multiple guest instances. Each guest instance is called a container. Within each container, we install the application and all the libraries that application depends on. The key to understand the difference between the hypervisor-based virtualization model and the container-based virtualization model is the replication of the kernels. In the traditional model, each application is running in its own copy of the kernel, and the virtualization happens at the hardware level. In the new model, we have only one kernel, which will supply different binaries and runtime to the applications running in isolated containers. So the container will share the base runtime kernel, which is the container engine. For the new model, the virtualization happens at the operating system level. Containers share the host's OS, so this is much more efficient and lightweighted. You might want to ask, what do we gain by running those applications in different containers? Why can't we just run all applications in a single VM? This comes through the nature of isolation. As you know, most applications depend on various third-party libraries. Let's say we want to run two Java replications with two different JREs. This is going to be quite challenging if you want to run those two applications in the same VM without introducing any conflicts. By leveraging containers, we can easily isolate the two runtime environments. Let's say application A requires JRE 8. Then we just install JRE 8 in the first container and run application A in the first container. For container B, it requires JRE 7. Then we just install JRE 7 only for second container and run application B inside the second container. In this way, we have two containers on the same machine running two different applications, each with a different JRE version. This is what we call runtime isolation. Comparing to hypervisor-based virtualization, container-based virtualization has some obvious benefits. Firstly, it's more cost-effective. Container-based virtualization does not create an entire virtual operating system. Instead, only the required components are packed up inside the container with the application.
Containers consume less CPU, RAM, and storage space than VMs.
That means we can have more containers running on one physical machine than VMs. Secondly, faster deployment speed. Containers house the minimal requirements for running the application, which can speed up as fast as a process. A container can be several times faster to boost than a VM. Thirdly, great portability. Because containers are essentially independent self-sufficient application bundles, they can be run across machines without compatibility issues.
That's it for this lecture. I'll see you later.
Let's talk a little bit about Docker's client and server architecture. Docker uses a client-server architecture with the daemon being the server. The user does not directly interact with the daemon, but instead through the Docker client. The Docker client is the primary user interface to Docker. It accepts commands from the user and communicates back and forth with the Docker daemon. There are two types of Docker clients: the typical command line client and Kidmatic, which is a Docker client with graphical interface. So if you don't like working with commands, Kidmatic is something you should check out. The daemon is the persistent process which does the heavy lifting of building, running, and distributing your Docker containers. Docker daemon is often referred as Docker engine or Docker server. On a typical Linux installation, the Docker client, the Docker daemon, and any containers run on the same host. You can also connect a Docker client to a remote Docker daemon, We will cover more about this later. But you can't run Docker natively in OS X or Windows, because Docker daemon uses Linux-specific kernel features. So on OS X or Windows installation, the Docker daemon is running inside a Docker machine. The Docker machine is a lightweight Linux VM made specially to run the Docker daemon on OS X or Windows. Let's get started on installing Docker on our local machine.
This lecture applies to you if you're using Linux or you're using Mac and your Mac version is OS X 10.10.3 or newer, or you're using Windows and your Windows version is Windows 10 or newer. Otherwise, you can skip this lecture and follow the instruction of the next lecture to install Docker Toolbox on your local machine.
Here we Google Docker install. The first entry is Docker's official installation page. Just click the link to enter the installation page. The steps required to install Docker vary depending on the operating system you use.
If you're using Linux, you can just follow the corresponding installation instruction on this page to install Docker on your operating system.
Since Docker is a technology built around Linux containers, people developing on non-Linux platforms would need to use some forms of virtualization to run Docker. If you're running Windows, just scroll down and click the Windows installation link. As you see, there are two options for installing Docker on Windows: Docker for Windows and Docker Toolbox. Now, if you have Windows 10 or a newer version installed, you will be able to install Docker for Windows. Docker for Windows runs as a native Windows application, and it has a built-in virtual machine inside the app, which saves you tons of efforts from managing the VM by yourself. Docker for Windows is the desired way to run Docker on Windows machine, as long as you meet minimum requirement. You can just click the Getting Started with Docker for Windows link to start the installation. Since I'm using Mac, I'll be demoing how to install Docker for Mac on my Mac machine. But the steps should be very similar between Windows and Mac. Here, I scroll down and click the Mac installation page. Similar to Windows, you also have two options here. You can either install Docker for Mac or Docker Toolbox. If your Mac is 2010 or a newer model, and the Mac version is OS X 10.10.3 Yosemite or newer, it is recommended to install Docker for Mac, which runs as a native Mac application. I'm running a relatively newer version of Mac. Here, I just click Getting Started with Docker for Mac.
Let's download the stable version. As you see, it is downloaded the installer.
I'm fast-forwarding the video until the download is complete.
Now the installer is downloaded. Let's click it.
Then drag the whale to the Applications folder. Just type your password to proceed. Then open the Applications folder and double-click the whale icon. Click Next. Now installer is asking for privileged access, as it needs to install its network components. Just click OK and type password to proceed.
Docker has been installed on my local box.
As you see, we have a whale icon on the menu bar on top of our desktop. This initialization phase might take a while to complete. I'm fast-forwarding the video until it's finished. This is what you would see if everything goes well. Now Docker is starting. Finally, we got Docker up running. Let's open a command line terminal. Then type Docker info. Docker info would display the system-wide information about Docker. As you see, Docker is running inside a Linux virtual machine. You can also configure your Docker preference by clicking the whale on the top menu bar, then select Preferences. Now we're under the General tab. Docker for Mac is set to automatically start when you log in. We'll leave this option checked so that we can have Docker automatically start when we log in into our desktop. You can also configure the number of CPU processors. You can increase processing power for the app by setting this to a higher number, or lower it to have Docker for Mac use fewer computing resources. By default, Docker for Mac is set to use 2 GB runtime memory, allocated from the total available memory on your Mac. You can increase the RAM on the app to get faster performance by setting this number higher. That's it for this lecture. I hope you've enjoyed it. In this lecture, we'll see how to install Docker Toolbox on your local box. This lecture applies to you if you're using Mac and your Mac version is older than OS X 10.10.3, or you're using Windows and your Windows version is older than Windows 10, or you want to install Docker Machine or Kitematic instead of Docker Engine. Otherwise, you can skip this lecture and follow the installation guide of the previous lecture. Here, we Google Docker install. The first entry is Docker's official installation page. Just click the link to enter the installation page. The steps required to install Docker vary depending on the operating system you use. If you're using Linux, you can just follow the corresponding installation instruction on this page to install Docker on your operating system. Since Docker is a technology built around Linux containers, people developing on non-Linux platforms will need to use some forms of virtualization to run Docker. If you're using Windows, just scroll down and click the Windows installation link. Then click Docker Toolbox. Then you can click Get Docker Toolbox to download Docker Toolbox installer for Windows. Since I'm using Mac, I'll be demoing how to install Docker Toolbox on my Mac machine. But the installation steps should be very similar between Windows and Mac. Here, we click the Mac OS X link to go to the installation guide for Mac. Then click Docker Toolbox. As you see, we'll be installing Docker Toolbox, which will install all the components you need to run Docker on Mac OS. Just be aware that you need OS X 10.8 Mountain Lion or newer version to install Docker Toolbox. Here, we click Get Docker Toolbox link. Then download the installer for Mac. The download is going to take a while. I'm fast forwarding the video until the download is complete. Now the installer has been downloaded. Docker Toolbox includes a minimum boot to Docker virtual machine, which will run inside VirtualBox. If you have VirtualBox running, make sure to shut it down before running the installer to avoid conflict. Let's double-click the icon to run the installer and accept all the default. The installer is going to install Docker Client, Docker Machine, Docker Compose, Kitematic, and Quick Start Terminal app. Docker Machine is a tool that lets you install Docker Engine on virtual hosts and manage the hosts with Docker Machine commands. Docker Compose is a tool for defining and running multi-container Docker applications. Kitematic is graphical Docker client. If you don't know what they are, don't worry. We'll talk about them in more details later. Type in the password to proceed. Now the installation is complete. Here we choose to start with the Docker Quick Start terminal. Now it is provisioning the Docker machine. The first time you run it, it would take a while. We'll just fast forward the video while the machine boots up. This is what it looks like if everything works successfully. This terminal is effectively a Docker client which takes the user input and send them to the Docker daemon. Here we can run Docker Machine ls command, which will last all the Docker virtual machines. As you see, we have our default Docker machines up. The Docker daemon is running inside the Docker machine. If you run Docker version command, it will print the version for both client and Docker server. Docker server refers to the Docker daemon. Here, if you launch the VirtualBox, you'll find out the installer has installed and configured a boot Docker VM, and the Docker daemon is running inside the VM. Before we finish this lecture, let me show you how to run Docker next time. Once you have the Docker Toolbox installed, you can access Docker anytime by opening the Docker Quick Start terminal again. See? We get back our Docker client. There are several important concepts we must understand before we start playing with Docker. The first two concepts are containers and images. Images are read-only template used to create containers. Images are created with the Docker build command, either by us or by other Docker users. Because images can become quite large, images are designed to be composed of layers of other images, allowing a minimal amount of data to be sent when transferring images over the network. Images are stored in a Docker registry, such as Docker Hub. We'll talk about it in a minute. Next, we'll talk about containers. To use a programming metaphor, if an image is a class, then a container is an instance of a class, a runtime object. Containers are hopefully why you're using Docker. They're lightweight and portable encapsulations of an environment in which to run applications. We create a container from an image and then run the container. And inside that container, we have all the binaries and dependencies we need to run our application. Here are another two important concepts about Docker: registry and repositories. A registry is where we store our images. You can host your own registry, and you can use Docker's public registry, which is called Docker Hub. Inside a registry, images are stored in repositories. Docker repository is a collection of different Docker images with the same name that have different tags. Each tag usually represents a different version of the image. Let's take a look at the Docker Hub. Docker Hub is a public registry which contains a large number of images you can use. Here we Google Docker Hub. The second entry is what we are looking for. Just click the link. Here we click Browse to see what we can find. As we see, there are some popular official repositories listed here, such as Nginx, Ubuntu, and Redis. Official repositories are certified repositories by Docker. For each repository, we can also see the number of stars and pulls, which indicate the popularity of each repository. You can also search other repositories here. Let's say we want to find some MySQL images. Let's type MySQL and hit enter to search. See? So Docker Hub found some MySQL repositories here. Note the first one is marked as official. New Docker users are encouraged to use the official repositories in their projects. These repositories have clear documentation, promote best practices, and are designed for the most common use cases. Docker Incorporation, which is the company behind Docker, sponsors a dedicated team that is responsible for reviewing and publishing all official repositories' content. It is also ensured that security updates are applied in a timely manner for official images. So when we get started with Docker, try to use official images so that we can get the most support from the community. All the other repositories are also MySQL repositories, which presumably contains MySQL images. They are contributed by other users in the community. So how can we tell which one is an official image and which is not? First of all, as we mentioned before, official images usually come with an official mark. Also, the name of an unofficial image usually has a namespace before the actual image name, which is often the username of the user who created the repository. Here, let's click the link of the official MySQL repository. We can see the information about this REPL and clear documents about how to use this image. If I scroll up and click the Tags tab, we can see the repository has several tags. In most of the cases, the tag means the version of the application or tool in this image. So an image is specified by its repository name and tag. Even the same image might have multiple tags. If you don't specify a tag, Docker will use the default tag, which is latest. We'll get into more details about this when we start playing Docker run command in the next lecture. In this lecture, we'll learn how to create and run our first container. We're going to create a container from an image. The image we're going to use here is called BusyBox. Let's go check it out. Here, we're at Docker Hub website. Just search for BusyBox. Let's click the first one, which is the official BusyBox repository. We quickly scroll down the document. As you see, BusyBox is a tiny image, which is only about 1 megabyte. This is the main reason we choose BusyBox, because of its tiny size, so it would take little time to download. Let's check out the Tags tab. BusyBox has various different tags. Here, we pick tag 1.24 to run our container. Let's close the browser and open the Docker Quick Start terminal. If you have installed Docker for Mac, Docker for Windows, or you are using Linux, you can just open up a normal terminal. When we use the image to create a container, Docker will first look through our local box to find the image. If Docker is able to find the image locally, it will use the local image to create the container. If Docker can't find the local copy of the image, it will download from remote registry. To find out what image you have in your local box, we can run the Docker images command. See, we don't have any images in my local box. Now let's start running our container. To run a container, we will use docker run command. Docker run command will create the container using the image we specify in the command line, and it will spin up the container and run it. As we talked about in the previous lecture, an image is specified by the repository name and tag. We need to put a column between the repository name and the tag. So let's use BusyBox image with tag 1.24. After that, we need to specify what command we would like to run in that container and pass the argument for that command. The command we're going to run is echo, and let's put the argument hello world. So the Docker should output hello world after spinning up the container. Then hit enter. As you see, Docker goes ahead and downloads the image from the remote repository. That is because we don't have BusyBox 1.24 on our local box. After Docker downloads the image, it will create the container from the image and run the container. See? Docker outputs hello world, which is what we expected. Now, if we run Docker images command again, as you see, we have one image, which is the one we just downloaded, BusyBox 1.24, and the image has a unique ID. When we run the container again, Docker will use local copy of the image to create and run the container. Let's see it in action. Notice how faster the execution is. It prints out hello world right away. This is because we already have the BusyBox 1.24 image in our local box. So Docker just creates the container from the local image right away, without the need to download the image from remote registry. Let's see another example. Let's say we want to display all the contents in the root directory of the container. Just do docker run BusyBox 1.24, then ls command /. There you go! Docker outputs all the contents under the root directory of container. We can also run container in an interactive mode so that we can go inside the container. We need another two options, -i and -t. The -i flag will start an interactive container. The -t flag will create a please-do tty that attaches standard input and output. Let's see this in action. Here we do docker run -i-d. We'll keep using BusyBox 1.24 again as the image. Now we hit enter. There you go. It gets me right inside the container. We can run ls command. See? It gives us all the contents in root level. Let's say we want to create a new file here called a .txt. After that, we do ls again. We can see the file is created. Now, we can type exit to exit the container. Note that once we exit the container, Docker also shuts down the container. If I run the same container using the exact same container run command, Docker will spin up a container. But this time, Docker starts a brand new container. So if I go check out the file I created previously by running ls command, you can see it is not there. As you see, when we run docker run command, it spins up a new container. The container we created previously with a text file has been shut down. Hello, and welcome back. In this lecture, we're going to deep dive into Docker containers. We'll learn how to run containers in detached mode, how to specify Docker container name, and how to use Docker PS and Docker inspect commands. In the previous lecture, we have seen how to run containers in the foreground. But in most cases, containers are actually running in the background. We can start a Docker container in detached mode with a -d option, so the container starts up and runs in background. That means we can start up the container and could use the console after startup for other commands. Let's see this in action. We'll keep using our BusyBox image. In order to keep the container running at the background, we can run the Linux sleep command to suspend execution for a while. Let's do docker run -d busybox 1.24 sleep 1000. Then hit enter. See? Docker returns us the long container ID. Now the Docker container should be running at the background. But how can we verify that? We can find out all the running Docker containers in our local box by using docker ps command. See? The container we just started up is currently running. As you see, the docker ps command displays some container information such as container ID, image name, and the command we run. The container ID displayed here is the short container ID, which is the prefix of the long container ID. What if we want to display all the containers in the local box, including ones which have stopped? We can add the -a option at the end of the docker ps command. See? Docker also shows all the containers that I have previously run. If we do not intend to keep the container, we can add rm option in the end. So the Docker would automatically remove the container when the container exits. Here we do docker run --rm busybox 1.24. Let's sleep for 1 second, then hit enter. The container runs for 1 second, then exits. Here we run docker ps-a to list all the containers. As you see, we don't see the sleep1 Docker container we just run because it has been removed by Docker as soon as it existed. Here is another useful option. We can also specify the name of the Docker container we want to run. Here we type docker run --name hello world busybox 1.24. Now, let's run docker ps-a to list all the containers. As you see, the new container is named as hello world. If we don't specify the container name, Docker will automatically generate a container name when we run docker run command. As you can see here, we get some funny name here, such as Boring Rosaline, Matt Lemire, and Kick-Ass Hopper. Before we finish this lecture, let me show you another handy Docker command. Docker inspect. Docker inspect will display low-level information on a container or image. Let's see this in action. Let's start up a new container in the detached mode. Docker returns us the container ID. Then let's run container inspect. Copy and paste the container ID and hit enter. See? Docker inspect renders the results in a JSON array. It displays the IP address and MAC address of this container. Let's scroll up. As you see, Docker inspect also outputs some useful low-level information, such as the image ID and log path. I hope you've enjoyed this lecture. I'll see you later. In this lecture, we'll talk about Docker port mapping and Docker log command. We'll be using a new Docker image, the Tomcat image. Tomcat is an open source web server that executes Java servlets. Let's check it out. Here, we're at the Docker Hub page. We search Tomcat and enter the official Tomcat image page. Let's scroll down. As you see, Tomcat page by default runs on port 8080. We can expose a port inside the container and map the port to another port on the host by -p option. In this way, the Tomcat web server can be accessed by using the host URL and the mapped port. If you're running Docker on Linux, the host here refers to localhost. If you're running Docker on Windows or Mac with Docker machine, the host here refers to the Linux virtual machine running Docker. The format for -p option is -p host port, container port. Let's see this in action. Here, we open up the Docker Quick Start terminal. Just make the font size larger as before. Let's do Docker run -it -p8888 column 8080 to expose the container port 8080 to host port 8888. Then Tomcat 80 and hit enter. Tomcat image is about 300 megabyte large, so it takes quite a while to download. It is recommended to run this Docker command when you have good internet connection. I'll fast forward the video until the download is done. Now the image is downloaded and the container is up running. We can access Tomcat server through web browser. First, we'll scroll up to find out Docker machine IP. Just copy it. If you're running Docker on Linux, or you're running Docker for Mac or Docker for Windows, the host IP is just localhost. Then we open our browser, paste the host IP, and go to port number 8888. See, we have opened the Tomcat console page. In most cases, especially in production, we would run containers in the background. Previously, we have learned -d will allow us to run containers in detached mode. Let's try it out here. Then we check the container status by running docker ps-a. As you see, our previous Tomcat container has existed. Let's go back our previous container run command and add -d option. Hit enter. See, Docker returns us the long container ID, and the container should be running at the background. We can check out the logs of running container by docker logs command. Just type docker log and the container ID. Oops, it should be docker logs, not docker log. Let's redo it again. See, we're seeing the container logs. In this lecture, we're going to talk about Docker image layers. A Docker image is made up of a list of read-only layers that represent file system differences. Image layers are stacked on top of each other to form a base for the container's file system. Take a look at this diagram here. Each image consists of multiple layers, and each layer is just another image. The image below is referred to as the parent image. We call the image at the very bottom as the base image. Docker is pulling the images layer by layer. You can also check the full set of layers that make up an image by running the Docker history command. As you see, BusyBox image consists of 2 layers. The base layer is to add a file, and the second layer is to run bash. When we create a new container, you add a new, thin, writable layer on top of the underlying stack. This layer is often called the writable container layer. All changes made to the running container, such as writing new files, modifying existing files, and deleting files, are written to this thin writable container layer. The major difference between a container and an image is the top writable layer. All writes to the container that add new or modify existing data are stored in this writable layer. When the container is deleted, the writable layer is also deleted. The underlying image remains unchanged. Because each container has its own thin writable container layer, and all changes are stored in this container layer. This means that multiple containers can share access to the same underlying image, and yet have their own data state. The diagram shows multiple containers sharing the same Ubuntu 15.04 image. In this lecture, we'll learn how to build Docker images. There are 2 ways to build a Docker image. We can either commit our change made in a container to make a new Docker image, or we can write a Docker file to build an image. In this lecture, we'll start looking at the first approach. Here is what we'll do in the lecture. Firstly, we'll spin up a container from a base image. Secondly, we'll install git package in the container. Finally, use docker commit command to commit changes made in the container to build a new image. Let's see this in action.
This time, we'll be using Debian Image, which is one of the most popular Linux distributions. Here, we're at the Docker Hub website. Search for Debian.
Let's pick tag Jesse.
As you see, Debian is also a relatively small image, which is about 125 megabytes and consists of 2 layers.
Open up our terminal
And type docker run -it debian jesse.
Since Docker can find the image locally, it is pulling from Docker Hub. I'm fast forwarding the video until the download is done. Now the image has been downloaded, and we're right inside the shell of the container. We can do ls command to show the root directory structure of the container.
As you see, it is typical Debian file system.
What if we want to use git command here? Just type git. Oops, looks like git is not installed in this container. Let's install it by using the apt-get package management tool. Here we do apt-get update and apt-get install -y git. We put -y here so it would automatically confirm yes to prompts. Now, as you see, it is installing Git. I'll fast forward the video until it is done. Now it has installed the Git package. Let's verify Git has installed correctly. First, we clear the screen and type Git again. See? Git shows me the help message. What I will do now is that I'll exit the shell and we're going to commit our container as a new Docker image. We have a new command to learn. That is docker commit. What docker commit command does is to save the changes we make to the container's file system into a new image. When running this command, we specify the ID of the container we're committing and the repository and tag of the new image. Let me show you in a second. Here we do docker ps-a to get the ID of the container we just run. Then we commit the container by running docker commit. Just copy and paste the container ID here. Next, we need to provide the repository name and image tag.
For the repository, I'll put my own Docker Hub repository name, which consists of my Docker Hub user ID, James Lee // and the official Debian repository name.
And we'll tag the image with 1.00. Then hit enter. Docker commits our changes to a new image and returns the long ID of the new image. If we do Docker images here,
we can see our new image, James Lee Debian,
and tagged with 1.00.
It's a little bit bigger than the official Debian image because I extended the file system.
We have learned previously, images are made of the file system layers.
The base layer of this new image is Debian.
And we have extended the base image with a new layer, so it takes a bit more size on disk. Here we can spin up a container based on this new image. Now we're in the shell of the new container. We can do ls command to show the file structure. Let's try the git command here. See? The git command has already been installed. The changes we have committed are persistent in the new image. I'll see you later. In this lecture, we'll take a look at the second approach to build a Docker image using Dockerfile. A Dockerfile is a text document that contains all the instructions users provide to assemble an image. What is an instruction? It can be, for example, installing a program, adding some source code, or specifying the command to run after the container starts up, and so on. Docker can build images automatically by reading instructions from a Docker file. Each instruction will create a new image layer to the image. Basically, instructions specify what to do when building the image. Let's go ahead and create a Docker file. A Docker file must not have any extension. It must be named as Dockerfile with capital D. The Docker file gets created. Let's open it up. We add our first instruction, from instruction. Docker runs the instruction in a Docker file in order. The first instruction must be from to specify the base image from which you are building.
Here, we just use Debian Jesse as our base image. So Debian Jesse is the argument for the from instruction.
The instruction is not case sensitive. However, convention is for them to be uppercase in order to distinguish them from arguments more easily. Let's move to the next instruction, run instruction. Run instruction will specify a command to execute. It can be any commands you can run in a Linux terminal. Here, we do apt-get update first. Then we install git. Make sure we put -y option, because we won't be able to answer the prompt. Next, let's install vim as well. Now we have our Docker file ready. Just save the file. It is time for us to start building the Docker image. We have a new command to learn, docker build. Docker build will build the image using instructions given in the Docker file. Here we type docker build. Docker build takes a -t option to tag the new image we're building.
As I did in the previous lecture, I'll tag the image with my own repository name, James Lee /Debian.
Docker build command also requires a path, which is the path to the build context. The path specifies where to find the files for the context of the build on the Docker daemon. For example, if we would like to copy some source code from local disk to the container, those files must exist in the build context path. Remember that daemon could be running on a remote machine, and that no parsing of the Docker file happens at the client side. When the build process gets started, Docker client would first pack all the files in the build context into a tarball, and then transfer the tarball file to the Docker daemon. What's more, by default, Docker will search for the Docker file in the root directory of the build context path. If your Docker file doesn't live in the build context path, no worries. You can tell Docker to search for a different file by providing a -f option. Here, my Docker file is at my current directory, so I can just use the current directory as the path. Now, we hit enter to start the build process. Let's go through the build output to get a better understanding about how Docker is building the image. First, it outputs sending the build context to Docker daemon. As we mentioned before, now the Docker client is transferring all the files inside the build context, which is my current folder from the local machine to the Docker daemon.
Step 1. From Debbie and Jesse. That is the from instruction.
As you can see, Docker is going through the instructions in the Docker file. Then step 2. Run apt-get update. Docker is executing the run instruction. It says running in, followed by a container ID.
What happens is that Docker starts a new container from the base Debbie image and is executing the apt-get command in the container.
Now, when step 2 is about to finish, it prints out removing intermediate container and followed by a container ID. You might have already noticed the two container IDs are exactly the same. So Docker spins up a new container and afterwards just removes it. Let me explain to you what is happening here. Docker daemon runs each instruction inside a container. A container is a writable process that will write file system change to an image. In our case, it installs a program. Once Docker has written changes to the image and committed that image, Docker removes the container. So, for instruction, Docker creates a new container, runs the instruction, commits a new layer to the image, and removes the container. Basically, containers are ephemeral. We just use container to write image layers, and once they're finished, we get rid of them. Images are persistent and read-only. Let's continue digging through the output. Now it says step 3. apt-get install -y-git and followed by a container ID. What happens is that at the end of step 2, Docker committed our container as a new image. And it starts a new container from that image for the next instruction. Now it is installing Git. When step 3 is about to finish, it is repeating the same process to commit the intermediate container as a new image and remove the container. Let's move to step 4. It says run apt-get install -yvm, and Docker is executing the command in a new container from the image it committed in the previous instruction. Once all the steps are finished, the build completes successfully. Let's run Docker images to make sure the new image is created successfully. As we can see, the image we just built is tagged with latest because we don't specify a tag when we run the Docker build command. The new image we created is about 250 megabytes.
The base Debian image is only about 125 megabytes.
The new image almost doubled the size of the base image. So the extra layers we added by installing Git and Vim are about 125 megabytes. That's all for this lecture. I'll see you later. Hello and welcome back. In the previous lecture, we have seen how to write a Docker file to build an image. In this lecture, we'll learn a little bit more about the Docker file syntax and some best practice to write Docker files. First of all, we'll take a look at how to chain run instructions. One thing to keep in mind is that each run command will execute the command on the top writable layer of the container, and then commit the container as a new image. And that new image is used for the next step in the Docker file. So each run instruction will create a new image layer. It's recommended to chain the run instructions in Docker file to reduce the number of image layers it creates. I'll show you how to do this in a second. Here, we modify the Docker file. Instead of having 3 instructions, we'll do apt-get update and apt-get install git, and Vim to aggregate those 3 instructions into one. Let's save the Docker file and rebuild the image. As you see, we have only 2 build steps instead of 4, which means it is only adding one more layer on top of the base image instead of 3. Another good practice when writing the run instructions is to store multiple line arguments alphanumerically. This will help you avoid duplication of packages and make the list much easier to update. Let's say we want to install Python package as well. We need to put Python between Git and Vim so that they're sorted alphanumerically. Now we'll move on to the CMD instruction. CMD instruction specifies what command you want to run when the container starts up.
If we don't specify CMD instruction in the Docker file, Docker will use the default command defined in the base image. In our case, it is Debian Jessie, and the default command is bash.
Unlike the run instruction, the CMD instruction doesn't run when building the image. It only runs when the container starts up. You can specify the command in either exec form, which is preferred, or in shell form. Let's see this in action. We modify the Docker file, add CMD instruction after the run instruction. Here we echo hello world. Let's rebuild the image. The build completes successfully. Now let's start a container from this image. Just copy the image ID here. See, it prints hello world. We can also overwrite the CMD instruction at runtime. When you do Docker run, you can specify a different command to run.
Let's rerun the container from the image
and overwrite the CMD instruction with echo hello Docker. See? This time it prints out hello Docker instead. The next topic we're going to talk about is Docker cache. You probably have already noticed last Docker build is much faster than the first build. That is because Docker cache. Each time Docker executes an instruction, it builds a new image layer. The next time, if the instruction doesn't change, Docker knows the image layer already exists, rather than building it again. Docker will simply reuse the existing layer.
As you see, the last Docker build does not redo step 2. It just reuses the image built previously.
This helps to make our build much faster.
If you're building many containers, this can greatly reduce build time. However, if Docker cache is used too aggressively, it may cause issues.
For example, say you have a Docker file like this. After building the image, all layers are in the Docker cache. Suppose you later modify apt-get install by adding extra package curl.
Docker sees the first and second instruction are not changed and reuses cache from previous steps. Because the apt-get update is not run, you can potentially get an out-of-date version of Git and curl. The solution is to chain the apt-get and apt-update command as a single instruction, so that whenever the apt-get command is modified, the whole instruction will rerun to ensure you get the latest version of the package.
You can also tell Docker to invalidate cache. by using the no cache flag when issuing the docker build command. Next, let's talk about copy instruction. The copy instruction copies new files or directories from build context and adds them to the file system of the container. Let's see this in action. Here, we add abc.txt file in my current directory. Let's modify the Docker file. Remove the cmd instruction and add a copy instruction to copy the abc.txt file to the container. Then save the file. Just rebuild the image and run the container. Let's enter the source directory. See? We get our abc.txt file. There's another instruction which is very similar to copy. That is the add instruction. Those two instructions are quite similar. The difference is that add can do more magic. Add allows you to download a file from internet and copy to the container. Add also has the ability to automatically unpack compressed files. If the src argument is a local file in a recognized compression format, then it's unpacked at a specified test path in a container's file system. Generally speaking, copy is preferred. That's because it's more transparent than add. Copy only supports the basic copying of local files into the container. Copy is really just a stripped-down version of add. Ultimately, the rule is this: use copy, unless you're absolutely sure you need add. I hope you have enjoyed this lecture. I'll see you later. Hello, welcome back. Previously, we have learned how to build a Docker image, either by manually committing the changes we made in a container or by writing a Docker file. In this lecture, we'll see how to push our extended images to a Docker repository so that other developers can use that image, or we can pull that to our production environment and run it as a container. The easiest way to make your images available is to use the Docker Hub, which provides free repositories for public images. First, we need to create a Docker Hub account. Let's go to Docker Hub, where you sign up for your account. Just type your Docker Hub ID, email address, and password. After you have signed up and you have logged into your account, it looks like this. I just created a Docker Hub account for this tutorial. JLead tutorial is the Docker Hub ID. In order to push the image to the right repository, we need to associate the image with the Docker Hub account. The way to link the image with the Docker Hub account is to rename the image to something like Docker Hub ID / repository name. The command to rename this image is docker tag. Let's see this in action. First, we issue Docker images command, which displays all the current images in my local box. The image we're going to push is this extended Debian image. Now let's rename this image. Just type docker tag, copy and paste the image ID. Then the repository name, jetutorial/Debian. We also need to specify a tag for this image. If we leave it blank, Docker will just use the default latest tag. But try not to use latest tag unless you have to. Let me explain why. Docker will use latest as a default tag when no tag is provided. But beyond that, the latest tag has no special meaning. A lot of repositories use it to tag the most up-to-date stable image. However, this is still only a convention, and is entirely not being enforced. Images which are tagged latest will not be updated automatically when a newer version of the image is pushed to the repository. If you're shipping Docker images to a production environment, you should just ignore the latest tag. Don't use it. Don't be tempted by it. It's easy to look at it and think that your deployment script should just pull latest. However, this is not enforced. It takes a lot of discipline to make that work. The safest way is just to version your tags every time. Here, we just explicitly specify tag 1.01. Then hit enter. Now let's do Docker images again. See? The image has been tagged with a new name. The first and the second image have the same image ID because they're the same image and have exactly the same content but tagged with different names. The next step is to push the image to Docker Hub. In order to do this, we need to issue the command docker logging. We'll need to type our Docker Hub account credentials. Now we're logged in. Finally, we can do docker push followed by the repository name and tag. And hit enter. Now it is sending the image to Docker Hub. This is 250 megabyte image, which might take a while to push. I'm fast forwarding the video until the image has been pushed. This is what you will see if everything worked out successfully. Now, let's go back to our Docker Hub account and refresh the page. We can see the new image appears under my account. Now we can click the image and check the image details, such as image tag.